Hey guys, welcome back. We're going to start a series or a unit, I guess, on AC power and also power factor correction. In order to do, power factor correction, we have to understand what's going on with power when it comes to alternating current. Like in level 1, guys, like life was super easy because, we thought that power was the voltage times the current, and it is in DC, right? And in level 1 we were learning about DC. But in AC it's a little bit more complicated, and the reason it's more complicated is because, not all our loads are resistive, right? We've got capacitive loads, and we also have inductive loads and resistive loads, and so power gets a little bit crazy. And in order to see, why power is crazy, let's take a look at the AC sine wave, and we'll look at the voltage sine wave and the current sine wave, and then we'll look at it for the different kinds of circuits that we might encounter out there, and then we'll start talking about power in another video. Okay, guys? So the first thing we could encounter with AC is, the easiest one, and that is the resistive, the load is resistive, right, guys? So let's say I had 120 volts here, and I got a little resistor there, and I wanted to look at the voltage and the current as sine waves. I could do that, right? So, here's my voltage sine wave, right, guys? And my current sine wave, because this guy is going to be in phase, right, guys? It's a resistor. The current is also going to be a sine wave, right? And it's going to be nicely in phase like that. All right, and that's pretty simple. Now, if we want to take a look at the power, and we know that power is the voltage times the current in the circuit, what I actually have to do when it comes to power is figure out the instantaneous voltage and the instantaneous current, multiply them together, and you'll have the value of instantaneous power right there. So right here, the voltage is 0, and so is the current. And if I multiply 0 times 0, I'm going to get, 0 power right there. And in fact, it's going to be 0 power here and here as well. And maybe I should label these. This is E, and this is I. So let's try to figure out, what's going on when things are not 0. And here I've got a current that's peaking and a voltage that's peaking. They're both positive. And if I multiply those two together, I'll get a positive value of power. It's going to look something like this, right, guys? And over here, when I look at these two, I see them peaking, but they're both negative peaks, and I've got a negative current, and I multiply it by a negative voltage. If I multiply those two negative values together, I'll get a positive value, and in fact, it'll be the same positive value as if I multiply these two together, and so right there, the power is going to look like this. Now, if I wanted to draw the power curve, it's going to look like this. Okay, guys? So even though the voltage and the current are going positive and negative, the power for this type of circuit here is going to be always positive. And, this is, moving your kilowatt hour meter, and so it doesn't matter if the alternation is positive or negative, the power is going to be positive all the time. And there's the lowest value, and there's the peak value of the power wave. And I could draw a dotted line right here, and that would represent, the average, right? Power right there. And that's what you'd be paying for, basically, the average amount of power that this resistor was using. Now, it gets just a bit more weird when my load is an inductor. Okay, so let's draw the inductor load, 120 volts, and this is XL. And let's take a look at the voltage, the 120 that we applied here, okay? And so the voltage looks the same, right? It's still the 120 volt sine wave, just like that. But this particular circuit causes the current to lag by 90 degrees. So and that's because it's an inductor, right, guys? So if I took the look at the current on a scope on this particular circuit, I would get a current that looks like this. All right, guys? Now, if I want to see what's going on with the power in this circuit, I have to take the instantaneous values of voltage and multiply it by the instantaneous values of current to try to figure out the instantaneous value of power. And have a look here, guys. Right at this instant, I got a negative value of current and a 0 value of voltage. So anything times 0 is 0. So the power here is 0. And in fact, the power here is going to be 0 because the current's 0 here. Here the voltage is 0. Here the current's 0. Here the voltage is 0. Anytime I multiply anything times 0, I have 0. So I know those are all zeros. The only thing I have to do then is try to figure out what's going on between. And here I have a positive value of power, or voltage, I should say, and a negative value of current. A positive times a negative is a negative. Neither one of these is peaking right there. Okay, so it's not too much power, but it's negative. I know it's something like that. There it's 0. Between these two, I've got a current that's positive, a voltage that's positive. Neither one of them is peaking, but I'm going to multiply them together, get something like that. If I look here, positive current, negative voltage. Positive times a negative is negative. All right, and right here, negative and negative. Neither are peaking, but two negatives multiplied together is a positive. And if I join these, what you will see, if I was a better artist, is there's our power curve, okay? And you'll notice that it is peaking, it has a negative peak and a positive peak. It's sometimes positive and sometimes negative. Now, the average is going to be a line halfway between here and here, just like it was here. So the average power in this circuit right there, that is the average power, okay? And what that means is this thing doesn't move your kilowatt hour meter, at all, okay? It's using a bunch of current. If this guy here was 12 ohms, that means that current is 10 amps, guys, and so is this one, right? 10 amps. It's going to be E over whatever is limiting current in the circuit. Both of these blue lines represent a 10 amp current. This one's using a bunch of power. This one's using 0 power. All right, guys, so this gets a little weird now. Now, this isn't really a very realistic circuit, and the reason it's not realistic is because it's strictly inductive. In real life, you would have a circuit that is, an RL series circuit maybe. And so just for fun here, I'm going to flip this over. I'm going to draw my RL series circuit, and we're going to take a look at what that would look like. We'll get a fresh page here. Okay, guys? Brand new fresh page. An RL series circuit, would look like this, right? Resistor, inductor. Let's put the 120 volts to it. Let's say Z here is 12 ohms, okay? So the sum of these two, whatever they are, 12 ohms. The current in this circuit, again, will be 10 amps. Same as this one, right? 10 amps, 10 amps, 10 amps. Okay, guys? So what does this look like when it comes to voltage and current and power? Well, the voltage is 120 volts. That's the easy part. Okay, so we got my nice voltage sine wave here. There's my E. The current is going to lag the voltage by something between 0 and 90, right? So here it was in phase, guys. Here it was lagging by 90 because I just had an inductor. Here it's going to lag by some value. I don't know what because I didn't give you enough details. Okay, it depends on what these two are, but we know it's going to lag. So let's just draw a lagging current in here. Okay, maybe like that. It's lagging by, looks like about 45 degrees today. Okay, there's your current. And if I want to know what the power on this particular circuit looks like, well, anytime the voltage or the current goes through 0, the power is 0. So power is 0 there, and there, right, guys? And so now we'll just see what's going on between. Look, negative current, positive voltage, negative value of power there. Look here, positive current, positive voltage. Multiply those two together, they're going to be positive. Look here, negative voltage, positive current. It's going to be negative. Right in between these two dots, negative and negative. There, join the dots, right? Carefully. Okay, so there's your power curve for this particular one, or power wave, I should say. Now, in all three instances, the average amount of power that the circuit is using is a line that's halfway between these two peaks. So something like this, okay? So there's the average power for this circuit. Now, 3 different circuits, guys. 3 different circuits, all drawing 10 amps. Lots of power. No power. Some power. All right, guys? And that's what makes all this stuff a little bit complicated, okay? So come back for the next video. We're going to start talking about AC power, the 3 types, and what to do about it. All right, guys?